Hi, in this video, I'm just sharing a few thoughts about the normal distribution as we wrap up chapter 6. Okay, so I'm going to open up the last couple of pages of the notes. So see if I can share my screen. Okay, good. All right, so now we have this very powerful tool, which is that if in fact we know, I'm going to slide back a little bit, if in fact we know what the distribution of a given variable looks like, we can answer a lot of questions. We can find 90th percentiles, we can find various probabilities of events occurring, right, regarding your variable. So a relevant question is, well, and how do we know? How do we know if something is normally distributed, right? So that's the question of the day. So let's go ahead and move forward to the 6.4 notes here. So I just want to let you know, you don't have any homework problems on my stat lab or in terms of written work for me regarding this material, but it is just really important that we have a chance for me to share this information with you. Okay, so one of the things that the big questions is, well, how would you know if a variable was normally distributed? And you might say, well, we could build a histogram. And if the histogram has a nice bell shape, then it's reasonable to assume a variable was normally distributed. And I would be 100% in agreement with you. However, the reverse might not be true. Like we might make a histogram and it might not look bell-shaped, but it could be that it was generated from a normal process, because that traditional bell shape of a histogram really takes a very large number of observations to become obvious. So there are other techniques to determine whether or not it is reasonable to assume that data was generated from a normal process. And that's what I want to show you, and really just show you this. So I'm scrolling down here. These are called normal probability plots. And what they do is they compare percentile values of points in your data with percentile values for points if the data were normally distributed. And that's probably all I really want to say about the underlying mathematical statistics of the normal probability plot. But I do want you to know how to use it. I want you to know that it exists, okay? So if the data, and here's a picture of a normal probability plot, okay? And according to this plot, this data, which is some measure of pain here that was generated from a normal process, because on this normal probability plot, the data seem to be scattered about the line, and in particular, mostly inside these bands here. So this is a normal, this pain level variable has a normal distribution, and here's variation. So this data came from pain and infections on some skin patients, and you can see that there's something going on here which doesn't look like it's randomly scattered about the line, but you can see really mostly within this band. So it is, again, a way that the normal probability plot can look when it is reasonable to assume the data was generated from a normal process. So both of these graphs, we can assume that, we can make that assumption. Why do I might be talking about it? Well, because if it's reasonable to assume that the data was generated from a normal process, then it sort of determines what procedures we can use in inferential statistics. So we're really getting right down there, right, in this boundary between probability and inferential statistics now. Okay, so here are some graphs from your publisher, actually, from some slides your publisher had prepared, and these are normal probability plots but they are generated from a process that is where the variable is not normally distributed. So you see the systematic variation from data being scattered about the straight line here. And here's another one. So different software system, and there's no bands here, but still we can identify this systematic deviation from the straight line. So both of these would have to say no to the question, is your data normal? Then the answer would be no. Okay, well, that's all I really wanted to say. I will see you in chapter 7.